hash is a function that lets us map data of a unique string to a hex of a certain size. That's why we were able to take a big file like this and describe it with a bunch of hex like this. Not only that, but a good hash function should be able to produce different results with even the most minute changes to the original data. There are a couple of well-known algorithms that we use to do this, and SHA1 is one of them. SHA1 is a cryptographic hash function designed by the NSA, so it was pretty good back in the day, but at the moment, however, it's pretty insecure. But all the SHAs operate in a very similar way, and this is the easiest one to explain. When I go to describe the other ones, it's not going to be as difficult once you understand the basics of this video. Before we start the main algorithm, there are a few basic things you need to know. Without making this too elaborate, think of binary ones and zeros as being the language of machines. So if you want to write 5 in binary, it's 00000101. You might see an operation like this. This means left shift by one place. In other words, move all the numbers one space to the left, and I get this, 10. Now if I left shift it again by one place, I get this, which is 20. And if I right shift it, I could go back to 10 again. Notice the way we shift, we eventually fill up more spaces with 0. In a circular shift, the bits shift off the edge and reappear on the other side. So if I right circular shift this, we get this. Here we are moving them to the left, but we can also move them to the right as well. A digit in hex can be represented by a 4-bit binary string. For example, A is 1010. A hex number like A103FE23 can be expressed as a 32-bit string like so. We can also translate those binary digits to represent a number like this. Now what we're doing here is translating between different number systems, base 2, base 16 and base 10. Basically the same number can be represented in all three systems and we can freely convert between them. Another thing you need to be aware of is the 3 functions we will use for creating the hash. They are called choose, parity and major, and they look like this. These are pretty important as well, as it's these functions that are the reason that it's really hard to unhash something. Think about some algorithm that was true if A or B is true. How do you know if it was A that was true or B that was true? You can't know this, and you would have to try both in order to see which one made sense. Now later you will see that when we calculate the hash, we mix the information up so much that trying to guess these answers would take a very long time. The main component of these functions are made up of exclusive ORs. Again, I don't want to dive too deep into this, but an exclusive OR means only one of the parameters are true. So if you get a binary value of 0100, exclusive OR 0100, you would compare the first 2 characters to each other, and if one is true and the other is false, we will give the result as 1. In this case, however, the result is a 0. And we do this for the rest, and we just get 4 zeros. Now if we take 0100 exclusive OR 1100, the result is 1000. But if we do 0100 and 1100, the result is 0100 because the 1 is the only bit that is similar for both. Once you understand how to interpret the symbol, solving for each function is very easy. I'll do a quick demo on solving major with 3 2-bit binary strings. So let's do x and y, which when we solve gives us the result of the first part. We solve x and z and also y and z. Next we solve the exclusive OR for the result of x and y and x and z. And we use the result of that and the exclusive OR with y and z. So the result of major in this case is 1 1. I didn't mean to make this look like Robot Joker or a robot with lips. Anyways, look, this is the answer. I think this will give you a good understanding with how we use these functions. Now obviously you can, and we do in SHA1, use larger size bit strings, but I think after seeing how this is solved you will have a pretty good idea what the other functions do. In order to show you how to work this out, I've had to compute a lot of large binary strings on my laptop, copy them onto a piece of paper and then onto the whiteboard. And despite what my wife says, I myself am not a computer, and until Dr. Noonan's son builds the positronic brain, Elon Musk gets the neural lace working, or I learn to hold my attention for more than 3 seconds at a time, the process of transcribing these binary digits may be prone to error. So it's quite possible that if you run one of these values through a conversion function, it may show something different. However, I don't think this will take away from the overall experience of understanding how SHA1 works. So go easy on me. The steps it takes are pretty interesting, and understanding it will help impress your friends, your work colleagues, and maybe that cutie you really want to talk to but you're not sure what to talk about. Well, this, my friend, is the video for you. This here is the overview of the algorithm. The big N is the number of blocks we iterate this over, and each block is 512 bits in size. First we will create the message schedule WT. Now the first 16 words are got by splitting up the block into 16 32-bit strings. The next 64 words are got by running a combination of already known words through the left rotate of the result. We then take the message schedule WT, which will have 80 words. Letters AT represent our initial hash values. We create a temporary variable that is made up from a 5-place left shift, plus the result of running B, C and D through one of the functions. Which function we use here depends on which range we are in. For example, the first 20 times through the loop we use choose, and the next 20 we use parity, and next major, and then parity again. We then plus the result to E and then to one of the constants, again depending on the range we are in, and finally to the message scheduled word we are on in this iteration of the loop. We then assign a new hash value in place of the old. For instance, E gets the last value of D, D gets C, and C gets a slight modification to B by rotate left 30 places. B gets A, and finally A gets the temporary value we just got. We then move to the next word in the schedule and repeat the process again. Once we have done this for all the words in the message schedule, we add the final result for A to E to their respective values in the original hash values. If there are more blocks, we repeat this process again with the new hash values we just computed. Once the whole loop finishes, we join the final hashes together for the final hash result. And let's see what this looks like with a simple example. First thing we do is initialize the 532-bit hex values. We will use these for calculating the final hash later on. We then want to create the message schedule. We take the binary from our 512-bit block and we split it into 32-bit words. These 16 words make up the first 16 words of our message schedule. In our case, our message is so small it's only going to have one block. So ABC as binary is 11000001, 11000010, 11000011. Then we add a 1 to the end to mark the end of our string. Then we fill the rest up with zeros to pad the message. Then we finally add the size of message in binary, which is in this case 24, to the final piece of the message. Now I don't want to spend time writing out all the zeros, so assume that the dots mean repeating zeros, and between 4 and 16 it means the other 13 words are just full of zeros as well. Now you can see most of these are made up of just zeros, except for the first word and the last word. So now for the 17th to 18th word, we are going to use the left rotation of the exclusive ORs of a combination of previous words to decide what the word will be. For example, the 17th word, we decide what value this will be by using a right circular shift on 17 minus 16, 17 minus 14, 17 minus 8, and 17 minus 3 bits. That's the 14th, the 9th, and 2nd, and the first word. And then we want to solve for the 18th word using the 15th, 10th, 3rd, and the 2nd, and so on until we've met up all 80 words. Let's take our 17th word and see what it looks like to solve this. So we have 14, which is all zeros, 9, which is all zeros, 2, which is all zeros, and 1, which is our ABC with zeros in the end. We get the exclusive OR of 9 and 14, we get all zeros. We get the exclusive OR of 1 and 2, and we get this, 1, 1, 0, 0, so on. And then we get the exclusive OR of the results of these, and we get the following. Now, once we have the following, we can left rotate. So we get this to this. So that becomes the next word in space 17. Now we do this until we have all 80 words. Now we start to calculate all the hash values for each of the initial hash values by processing that block within this procedure. Now this isn't that bad. All it's doing is passing the values around and transforming the values through the functions we described earlier. For example, for A, we do a right circular shift by 5 places on the value, so we go from this to this. We add this to the result we get by passing B, C, and D through our function. For example, on the first run through, it'll be run through the choose function, X and Y, or not X and Z. 21st would be run through the parity function, and so on. But our result for this will be this. We then add this result to E, and we add this to the appropriate constant K in its binary form, which is first value in K, and add this to the message schedule for this point. We then reassign the values of all the other variables. E gets the value of D, D gets the value of C, C gets the left rotate 30 places of B, B gets A, and finally A gets the value of the temporary variable we just created. We then sum the values of A, B, C, D, and E to the initial hash values. For example, the initial hash value of A was this, and we add this to the final hash value for A, which is this, and we get this. And we do the same for B, C, D, and E. The final step then is to convert the 5 final variables to their base 16 representation and concatenate them together. I just want to clarify here that the hex in blue is the final hex of the E variable after running through all 80 iterations of the loop. Now before we got this, for each iteration of T, the current E variable was changing by adding its current value to the last value. That's what E plus HI minus 1 is doing. Don't forget, I could at any time convert the 32-bit hash at that interval of T to its hex value, but it makes more sense to show you the final result because this is what we see as the SHA1 of ABC. So that's pretty much it. The only thing to be aware of is that when you have a message bigger than 512 bits, you will have to iterate over the first loop more than once, but this should give you a pretty good idea of how the hash works. Okay, so thanks for watching my videos. If you liked it, please press like and subscribe if you'd like to see more videos, and please comment below with algorithms that you would like me to try to explain or butcher like this. Alright, all the best and good luck.